consider half research. Okay. Now, when you do all channel PWM, you basically now change the scheme where you have got now current reference. And now you also have a current feedback. And this current feedback is coming from here. Okay. Now you have here, you have got KP, whatever compensator you have, and this will generate a duty cycle. Okay. This duty cycle command is fed to your PWM generator, and it will generate an output and a complementary output. So this is going to go here and here. Okay, this is basically one phase. This is, let's say, phase A. Right? So based on this reference, now in this reference will look like this. Depending on however you want the reference to be. So now, these are PWMing at all times because you're trying to correct for this reference. Okay? So, your feedback here, if the feedback does not match your reference, it's going to continue to trigger the PWMs. So, all channel PWM, you end up having current sensors right in the winding. See, compared to, just contrast this with I have got this logic box. Okay? I have got Hall sensor input here, and I have got, based on the Hall sensor position, I basically fire commands. Right? What are those commands? Those commands are whatever, we have A top, B bottom, right? So you could have a command like, just like a space vector. You configure your converter in one shot. Boom. Right? Hall sensor comes in, you fire your converter. Boom. Right? So here you are configuring your inverter in one shot. Right? And your feedback current is, you could have it here. Right? And you can say, well, now I can couple this with a PWM, or let's say I have, couple with a PWM, and I have got some here feedback loop, right? But you're firing your inverter, in one shot. All states, all six switches are fired in one shot. So here you now have independent control of each phase. Does that make sense?
So for 3 phase, if you consider complementary switching,
yeah.
So that would be plus all switch.
Also, yes. Yeah. If your complementary switching is all channel PWM. Okay, now you can configure, if you're using a microcontroller, you can configure the switches to be however you want them to be, depending on your PWM driver, right?
So then high side and high and low side PWM, what's the difference?
So the difference is, you still do this, you're still doing this, right? So when I have got 8 off, when I'm only PWMing during these times, the inverter state is still configured by my hall sensors, right? Inverter state is configured by my hall sensor. So when I fire these, I basically also run PWM signal. Right? Does that make sense? Clear? So here, so think about one of the beauty of six-step control is your states are well defined, right? Your states are well defined. I know my A top is going to be on at this point in time. Whereas it's random when it comes to all channel PWM because it's going to respond now directly to your reference. So here, if you look at, in this case, what is the PWM sequence going to look something like this? There is no gap in all channel PWM. You basically have got pulses all the time. Even during this time, you'll have pulses.
How are we going to two high sides and two low sides?
So now here, when you say two high side and two low side, essentially you have got still now I can have, let's see. See here, we control so the idea really is that let's see if I can have I'll think about that. I'll think about that how to do it.
Because if we control two players of the term can simultaneously run, then there is no multiple stall or. Isn't it simply more of a field-oriented control?
No. This is not figure control. This one here, two high side, two low side, is see, if you look at your six states, what I believe we do there is, if you look at your six states, so you routinely take two high sides and two low sides in sequence. Let's see. Okay, so when these are my states, right? This is my inverter state. Basically, this is my inverter state. For 1, 0, 0, I have got A top on, B bottom on, right? Right? Now, A top on, B bottom on. So I have got, I'll think about what we did there.
And are those PWM schemes related to means only related to this six-step control, or those are the general PWM schemes?
No, these are only related to six steps. Except for the last one. The last one is common to sinusoidal plus trapezoidal. All of these are related to six steps. Now you can talk about space vector modulation, but this is purely related to six step control. Right? Now high speed So for tomorrow, we'll start with large signal model. Now what I have shown you in simulation is the small signal model, in the sense that we are dealing with PWM schemes. Now, and tomorrow we'll start with large signal model. Large signal model, we don't deal with actual switching, right? The advantage of large signal is that we are able to get the model performance much faster. We have run the simulation much faster without having to deal with individual switches. So we'll start with that, and then we'll move on to space vector modulation. Sinusoidal, yeah, we'll do sinusoidal control. That should take a few minutes. And then we have space vector modulation, and then we have field-oriented control. Now, all of these are also implemented in PSpice. Now, PSpice implementation and Simulink implementation and storage implementation are pretty similar in nature. So once you understand one, you should be able to understand other. So we'll cover those in the morning. FOC fundamental. That sounds okay? Yes? Okay. All right. So, and then we'll move on to some of the remaining things we skipped today. And then we'll try to wrap it up by 5 or so. Okay. All right. Any last minute questions? What do you mean by that? Yes, we have got, we have slides for stability analysis. Okay, so we'll talk about stability analysis, and we can talk about speed control and torque control. That should not take much time. We'll talk about that. And but once you understand the stability analysis, then I think torque control is current control, right? That's a single loop system. Speed control is dual loop. You have got outer loop plus an inner loop, right? So you have got the torque control is inherently single pole, right? So it is inherently stable. All you have to worry about is how fast can you control the current, how fast can you establish the current in the line. Speed is a little bit more challenging because now you have got two loops in cascade. So we'll talk about the stability analysis. How do you look at the system? How do you evaluate the body plot? How do you compensate it? Okay, what else? Yeah, I know it's a long day, and lot of information being thrown at you rapidly, randomly. It's not easy to absorb all of it. So I think if you guys have time, reflect at what you have learned today, and shoot back some questions tomorrow or some email, so we can have a continued learning process. So if there are no other questions, let's call it a day, and we'll start here tomorrow bright and early at 9.